All right, so kind of pick up where we left off. What should you have had done before today's class? With our last assignment, we had that Learn Smart, Chapter 3. On Friday as well, one thing I posted, if I can get over there real quick, is kind of that first Connect assignment. So you'll see it's kind of due in about 2 weeks from last Friday. We should have most of them, we've covered the material that you should be able to get through, I think around 9 or 10 questions. By the end of probably Wednesday, but for sure by the end of the week, you'll have everything to get through all the questions. So I would suggest start working on it now, working on it early, get those first 10 questions answered so the material's not even further removed kind of from your mind. Other than that, some other things to kind of mention before we hop into it. I'll be putting you up another online quiz after class today. If you follow along today, it should be pretty easy, 2 questions. That'll be due before we start class on Wednesday, okay? Any questions for me before we get going here? I was trying to get housekeeping stuff out of the way. So let's go down here. So we left off last class. Let me see if I have kind of a summary I had down. So let's kind of go back. Let's open up last week's lectures and just kind of remind ourselves where we left off. So come down here. We did things like calculate population, sample variances. We kind of worked through what that would look like. Now, one thing we kind of skipped over was this fun through variance in these slides right here. So we left off with this equation, right, to calculate our variance. So we went through every single observation. We subtracted the mean and squared that deviation or difference from the mean, wrote that number down. We did that for every single observation. We then added them all up and divided by the number of observations we had. Okay? So I'll pull this back up in a second, and we'll kind of look at this in Excel just to kind of see that there are actually 2 ways in which we can calculate the variance. Okay? And we can kind of decide which ones we think are easier once we look at it in Excel. So we started out with this equation. Now, if we want to look at the sample variance, the only thing that's going to be different is instead of dividing by the total number of observations, we divided by the total number of observations minus 1. Right? Now, you can rearrange that equation to look something like this. So if we start out here, there's a mathematical proof that can get you to this formula. You could argue this formula is a little bit easier to work with, and really it's up to you which one you would want to use. I think procedurally this one's easier to remember, and that's why I kind of teach it first. But I'll show you how we would use this method as well. So all this means, right, is take every single observation, starting with the first, I equals 1. Square every single value. Once you've done that for every observation, add them all up. Then if you subtract the number of observations times the mean squared, that actually gets you the exact same thing as this formula. So, you could do the same thing with the population variance. It's going to be the exact same formula, just instead of the sample mean, you're using the population mean. Instead of the number of observations in your sample, number of observations in your population. The only real difference there is instead of dividing by n, for the sample, we divide by n minus 1. Or, we said last week, dividing by a number is the same as multiplying by 1 over that number, okay? So, here's the proof, and this is, not something I'm ever going to expect you to recreate or reproduce, but if we wanted to, there is a mathematical proof to where you kind of start rearranging things. They do kind of a tricky thing in right here, where they multiply by n over n. Well, that's just multiplying by 1, it doesn't change anything, but it allows them to kind of rearrange and prove that this is, in fact, the exact same equation. So I always hate just kind of telling you, like, yeah, these 2 equations are the same. There is a reason why. Here's kind of the math behind it, but I don't want you to necessarily have to reproduce or kind of have an understanding of that mathematical process. Right? This isn't a pure math course, okay? So we just know that these 2 equations should be the exact same thing. Right? So what I could do is go back to that kind of head football or the football coach data set. Instead of the old method of the population variance, the thing that we need now is the sum of our values squared. So we could go through every single salary and just square it. Now when we add all these up, right, we would have this component. We already calculated the mean, I think it was 134.5 maybe last class. Plug that in, we had 10 observations. And that should give us, so we've got the sum of the x's squared. We know what the mean is. The mean squared would be this value. Now it's just a matter of plug this in here, so the 328,000, 10 observations times that mean squared. We get 147,000. We still need to divide by or multiply by 1 over, right? So divide by n minus 1 or multiply by 1 over n minus 1. If we do that, so we still have to divide this by 10, we get the exact same answer we had last class, okay? So this is no different, it's just a different method of calculating the same statistic, right? It should give us the same value. So we'll kind of walk through in Excel, another example here, just to kind of get some different look at it. So we'll kind of come back to this. Oh, what do I want to do? So I'll just pull up in that COVID blank file that we've been working with. And we had a bunch of work done here on the file that we saved and the completed file that's up there on Canvas. So I'm just going to work with this unemployment rate variable because it's a little bit smaller and maybe just kind of easier to see, okay? So the first equation that we had, going back to last week, to calculate the variance looks something like this. Now we're just going to treat it like it's a population data set just for the ease of we're just going to be dividing by n, right? Instead of having to worry about n minus 1 for the sample. So we're going to go through every observation, subtract the mean. Once we've done that, square that value. Once we do that for every observation, add them all up, and then finally divide by the number of observations we have. So if we talked about last class, just as kind of a check, and no one's yelled at me yet, but let's zoom in a little bit. Okay. Let's say we want to do our check. So let's do var.p. I mentioned last class, we use the var.s or var.p equations to calculate the variance in Excel. So we're treating this like a population data set. We'll select the variable. We know this is the variance, okay? But we can go through and kind of do this step, like the intermediate steps, just to kind of help us be able to see it a little bit better. So the first thing we needed was we need to take every observation, we need to subtract the mean, and we need to square that value, okay? Well, I can do that pretty easy in Excel. So here's my first observation. I want to subtract the mean. We don't have the mean yet, so that was kind of a flaw in my plan. So I'm going to go over here. Let's just calculate the mean over in this cell, all right? So the equation we used for that was just the average function, all right? So I'll calculate the average of this variable, Control-Shift or Command-Shift on a Mac, hit the down arrow. Now I've got my mean over here, I can start using that instead of like typing the number in. So I'll say, okay, I want to take this first observation, subtract the mean, and then to square something in Excel, you just use this little caret and then kind of whatever you want to raise to the power of. Usually we're just going to raise things to the second power, right? We're just squaring it. Okay? Now, when I copy this down for every other cell, I want to use the next observation. So instead of B2, I do want to use B3, and I do want to use B4. But I always want to keep subtracting that same mean, right? So I'm going to freeze this cell with those dollar signs right in front of the row and column heading. But now when I copy this down, it should take the deviation from the mean for every single observation, square it, right? So I've got the first observation. I'm just going to left click when it goes to this little black arrow. I'm going to drag this down to the bottom. And now it's done it for every single observation for me, okay? At the very bottom, I could think about this as maybe this is my sum of x minus the mean squared. Right? So I'll go use that sum function in Excel. I just want to add up all these values. I'll select all the values I want to add up. Right? So add up my entire, that new column I've created. Now I've got my numerator for that variance, the sum of the deviation squared. The only other thing that I should have to do is take that sum of the deviation squared and divide it by my total number of observations here. Well, I didn't calculate that yet, but I wanted to show you something else we can do in Excel. So a lot of the times I break things down into parts just because it's a little bit easier to see, but you can actually do everything in one cell. So notice here, I can take C18 and I can divide it by, and I can use another function. Okay? So I'm going to use that count function, which we said just counts the observation if it has a value in it, right? So I'm just going to count the original variable, and then that should return to me the total number of observations, right? And I don't have to do that in another cell first. I can do that within, right? It'll use this function and then perform the math, right? Dividing C18's value by whatever that count function returns. Hit enter, 3.94565. Sure enough, we'll get the exact same answer, right? So we have this built-in var.p formula, which is probably what we'll in practice use. But in case we ever wanted to kind of do the behind-the-scenes work, that's pretty easy to do in Excel as well. Okay? Now, the other method that I just kind of showed you was this formula. So we want the sum of the x's squared here. And then we want to subtract the number of observations times that mean squared. Okay? So we'll go create another column. And actually, I don't know if we've done this yet, so kind of a quick, helpful. You notice how my title's kind of running over here? If I just go between these two columns, C and D, and I double left click when I get this black double arrow, it'll auto adjust, so it just kind of makes it a little bit easier to look at. So here we want to just take the value for x and square it, right? And we want to do that for every observation. So I'll take the observation and I'll square it, right? Raised to that second power. Now, another nice trick is, instead of dragging this down with my mouse, this is a small data set, so that's easy to do. Notice when I kind of hover over this little green box, how my arrow goes to like a black plus sign. If I double left click, it'll automatically copy it all the way down to the very last, where the column next to it has like the very last entry. Now, here, this is not data, this is some stuff we calculated, so we'll get rid of that. But notice it copied it all the way down to the last observation formula. So that's kind of nice when we have a huge data set, okay? So I now have every x value squared. What I'm gonna do here, and let me insert another column. So this is gonna be the sum of the x's squared, right? So I'll just equal sum, and I'll select this column that I just created, which was like every single value squared. I'll move this out of the way. So that gives me the first part of this equation, right? The sum of the x's squared. Now I need to subtract the number of observations times the mean squared. So I go back here, right? What I can do to get that is, so I wanted to take that value I just found. I then wanted to subtract the number of observations times the mean squared. Well, I don't have it in another cell, but I can use that count function again, right? I can just count the number of observations in this data set. That should give me n. I then need to multiply that by the mean, which I had up here. And that'll automatically, when I click on it, just puts the cell reference in there for me. And I need to square it. The very last thing we need to do was divide it by the total number of observations. So I'm going to go back, put parentheses around all of this, and just divide by, once again, I can use that count function. And here it probably would be a little bit easier if I would have calculated the number of observations and then just clicked on that cell to reference it. But I just wanted to show that you can do it all within one. So it doesn't have to be this long. I could have broke this down and put the number of observations in another cell. So instead of using that count function, I could have just been using like the cell reference for wherever I did that. But this should give me exactly the same thing as I had before. Now this one's out to a few more decimals. I could extend that and we'll get the exact same thing, right? But it's really just two methods of getting the same answer. Or I can just use that shortcut and use fvar.p. But even using this variable, I can show you that either method should get us to the correct answer. Now, whichever way you think is easier to remember or whichever way you think is easiest to kind of compute by hand, that's probably the way that I would say to remember the variance. I think this way, the way I taught it last week, I introduced the variance with that because it really shows you what's going on behind the scenes, right? It's really showing you kind of this difference from the mean and how that gets over penalized if we're very far away, and how it helps with this idea that the variance is really some measure of like the average distance of each observation from that middle point, right? The way that first equation is written, that kind of reflects more that idea and that definition of the variance, okay? The second one is just something that's a little bit easier to do if you actually had to do this not with Excel but by hand. It's a little bit easier to add up all the squared values. And so used to be when you had to do this by hand, the reason why this formula, this mathematical proof exists is because this is a lot easier to deal with when I'm adding numbers up by hand and actually doing this without a computer, okay? Any questions on that? I went that over a little bit quick, but I think it's because really I wanted to kind of, this is the way that I think most people will remember it and should remember it, but there is another method out there. Now, if I remember right, we kind of went over this last class, right? I kind of talked about difference in means, shifts the distribution. We talked about how variances kind of can flatten the distribution if we have a lower variance, or sorry, a higher variance that flattens the distribution, lower variance kind of peaks it. So it should be about where we left off. And we kind of have this nice summary of all those different, like once we got past the histogram, any measure of central tendency or any measure of dispersion we talked about, we kind of have a nice summary of the Excel equations that go with it, okay? So a little bit of review, a little bit of new stuff. The next thing we're going to talk about is group data. And when we have group data, we're going to have to move away from calculating things like we did before, and we're going to have to do a couple of different things, okay? So it's going to be really similar to what we did before with the mean and the variance, but when we have group data, we're going to have to use some weights, right? So we'll be calculating things like weighted means and weighted variances, all right? So previously, really what we were doing is giving every single observation equal weight, right? And I'll come back to this and show you why in a second, but we were giving every single observation equal weight because every observation was just one subject, one country, one person, one whatever it was we were looking at, one state. However, what if we don't want to do that, right? So sometimes, right, we might have an example, and I don't like this example as much. I'm going to change it on the fly today. So we were looking at that COVID data set before where we had the number of cases by each state, right? Well, there, do we really want to just simply take the average, right, or the mean? Because even though I have a total number of deaths in California, right, that state represents way more people than the state of Delaware, right? That if we're doing things at the state level, California, that number represents way more people than it does. Let's say we weren't looking at the number of cases of COVID. Let's say we were looking at, I don't know, the average life expectancy in each state, right? Well, that one number in California, represents millions and millions and millions of people, whereas in Delaware, I don't know how people live in Delaware. I don't know, a couple 100,000, I guess. I don't even know if they have 1 million people. So we shouldn't be treating them both equally, right? Maybe I can use that population to weight California a little bit more than the value I see for Delaware, okay? And the other idea here I had was like large fast food corporations versus like some kind of a local, maybe like Berkey's or something like that. So the equation that we're going to use when we have this group data, so ideally, right, I would be able to see every single person's, like how long every single person lived as an individual observation. But all I can see is the average life expectancy for each state. So I've got this group data. What I could do is just take for every single state, I would take their life expectancy, multiply it by the weights I want to use, which probably makes most sense to use their population, right? So take that state's population, multiply it by that state's average life expectancy, do that for every single state, and then add them all up. Once I've done that, divide by the sum of my weights, okay? So why does this kind of get me this nice weighted means? So let's see if we can get this to work for a second day in a row. So it might take a second here to load up. There we go. Does this help or does this make it worse? Kind of helps, I think. So we were talking before, this was the equation we had for our mean, right? This was population mean. I could rewrite this as x1 plus x2 plus x3. Right? We're just adding up the values for every single observation and then dividing by the number of observations we have. Well, if I rewrote this and I just distribute the n, I could actually think about this as x1 over n plus x2 over n plus x3 over n, and so on. If I pull this out front, I could actually think about this like this, right? Where each observation is just 1 over the total number of observations. We can kind of think about it as that these were the weights we were using before. We weren't really seeing, like we weren't calling them weights. We weren't really, you don't see them in the equation. But really, if we rearrange this, we are weighting every single observation by the exact same. And how much do we weight them by? Well, they're just 1 out of the total number of observations. Okay? So let's say instead we only see kind of with some group data. Now, I don't know, maybe this is as simple as having 2 groups. Okay? And let's say for one group, let's say we have 20 individuals, and for the second group we have only 5. It only represents 5. But whatever variable we're looking at, so maybe we could go back to life expectancy or whatever we're interested in here, that whatever value we see for that first group, so let's say it was, I don't know, 10, that represents 20 people. Well, let's say we only see, I don't know, something like 1, but that only represents 5. Well, we don't want to just simply take an average of these 2 values because we know this value represents way more people. So what we said we would do, we can kind of use these as our weights. Right? So what we wanted to do is for every observation, multiply the weight times that x value. Right? And the reason why we're doing this, we can think about now, when I add these up, so I've got 20 times 10 plus 5 times 1, and then I divide by my total number of observations. Okay? Well, here, when I say total number of observations, it's not 2, right? It would be the sum of my weights because really the data reflects 25 different people. I can't see them individually, but these two values represent in total 25 people, right? So if I add my weights up here, well, let's think about it. If I rearrange this a little bit, so I've got 25 as my denominator. What I'm really saying is 20 over 25 times 10 plus 5 over 25 times 1. So what that formula does is it's saying, well, look, I see these 2 values for this variable x I'm interested in, but I know they represent way more than just 2 people. How much, or think about what proportion of the total people does this value of 10 represent? Well, 20 out of the 25, right? So by using this equation, what we're really doing is say we're going to weight that value of 10 by however many observations it represents out of the total, 20 out of 25. Then we'll add to that the second value we see, but what proportion of our total number of observations does it represent? Well, 5 out of the 25. So by using that formula, we could break it down, rearrange it. What we're really doing is we're just saying, how many observations does this value represent out of the total in this group data, right? It's just a little bit different because we don't see 25 different observations here. They're kind of grouped into 2 different groups, okay? Any questions on that? You see this okay? If you have any questions anytime I'm writing theory or something's not clear, let me know. It obviously looks a lot more clear to me probably than even to you, so. Okay with that? All right. Also, I haven't heard anything from people on Zoom, so if anything goes wrong there, let me know. You should be seeing me working through some stuff on, I don't know what to call this. I'm writing on paper on the dot cam, right? So, okay. I'll take the silence as though we're good. So, let's go back. There we go. So this is our weighted mean equation, right? We kind of have an idea about why we're using it now. So let's look at a couple examples, right? Well, I guess I have here in words what I just kind of already explained, but the first thing we're going to do is we're going to go through every single observation, multiply the value that we see for that variable by its weight. Right? We're then going to add all those up and then divide by, well, I guess we can add up all the weights and then finally kind of divide that sum of the weights times the values of the variable, divide that by the sum of the weights. So let's look at kind of an example. I pulled this data, where are we at with time? Okay. I pulled this data from the, U.S. Census Bureau. You can go online and you can create your own tables. You can break it down by a bunch of different things. Race and kind of gender are kind of usually the ones they put out there. to kind of see any disparities that exist in racial income or income across the races and income across gender. Right? So here's this group data. So each one of these mean income amounts, right? This is kind of the average income for white males, and this is the average income for Asian females. Yeah. Oh, you guys can't see it. Instead of raising your hand, you can shout at me or something next time, or say, "Hey, we can't see it." Let's see if we can get it up here. There we go. All right, so did I skip anything? So here was that kind of slide. It kind of just says in words what we're doing with this equation. Okay. So I grabbed this from the Census Bureau, right? And just because everyone in class couldn't see that. So this is the average income of, say, white males. Here's the average income of Asian females, right? We have group data, right? We only see one value for each group. Now, in this data set, these numbers, right, these kind of represent how many people this income value is representing. So for kind of black females here, that average income value represents 14,000 people. So this was actually not population data. Clearly, we don't have every single person in the United States. So it's a pretty big sample, but it's still a sample data set. Okay? So what we're going to do, right, to calculate what the average income is in the US based off this sample is, well, we have these observations that represent a different number of people. So we need to do a weighted mean, right? So let's say I just want to find the average kind of male income here, right? Well, I've got 4 groups, right? The kind of Census Bureau, however they define race. I can't remember all the exact, I think it's usually just self-reported. What we can do is say, well, look, all these incomes need to be taken into consideration. But we can see that some of these groups have on average a higher income value, right, than the others, right? But some of those values represent way more people, right? So this 59,000 represents 73,000 people, while this 60,000 only represents 6,000, right? So this observation shouldn't carry as much weight in our weighted mean as this observation should, okay? So what we're gonna do is just follow that process. The numerator is just taking every single observation's value, so here 59,000, multiply it by the weight that we're going to use for that group. Well, the number of people in that group, 73,000. I'm rounding here, but you know. So 59,000 times 73,000. Go down to the next observation, take its value, 38,000 times there's about 12,000 people in that group. Next group, 60 times 6,000, 36 times 17,000. Once we do that for every single group, add them all up. That'll be our numerator. We then divide by the sum of our weights, which conveniently here, I've already kind of put up there in the table, right? So here, the sum of our weights, we had a total of 108,000 people. We add up those frequencies or those weights, okay? So that's really just what I have written out here. You can do this and you can break it down and do it right next to the data, or you can just do it all on one equation, all on one line in your calculator, okay? We can do the exact same thing for female income. In fact, I think I kind of had these hidden. You open up the PDF, you can, let me see if I can get out of here. Here we go. So if you're just looking at this and you don't have it in like slideshow mode, you can just move. There's just white boxes over these answers just so we couldn't see them ahead of time. We could go ahead and do this for female. So what I'm going to do right now is just copy this and show you how we could do this very quickly in Excel as well. So I'm just going to create a new sheet. I'm going to paste that data. I'm going to blow this up so we can see it. And then show you, like, look, a lot of this class, like, we're not doing in-person exams, you're doing the homework on your own. If you want to get really good at Excel in this class, it's probably going to save you a lot of time and like help you out a lot, right? But in order to know how to use Excel, we have to understand, like, well, we need to know the statistics side before we take it to Excel, right? So we know that for the weighted mean, what we want to do is go through every single observation. Oh, sorry. What am I not hitting? I'm not hitting my W. There we go. I'm hitting 2. So I'm going to take my weight and multiply it the value for whatever X variable I'm interested in for every observation. So I just want to take the weight and multiply it by that income value. Okay? And I want to do that for every single observation here. But when I copy this down, it'll go from A3 and B3 to A4 and B4. Well, that's what I want, right? So that's pretty nice. So I copy this down. That was where I just left click when I get that black arrow, drag it down. I've now got the weight times the variable X I'm interested in for every single observation. So to get my numerator, we said we're just going to add those up. In Excel, use that sum function, right? I hate that auto does that. So I added up those values. That should be my numerator, right? So then to get my weighted mean, what should be in my denominator, right? Well, I had that total value up in the slides, but if I didn't have that total value, what's a way I could do that in Excel? Yeah. Exactly, right? I can just write that sum function in there, highlight these, now it'll add them up for me, right? And then I get my weighted mean, right? So notice, it's about 32,000. So some of these lower values of 24 and 28, the reason why the weighted mean is quite a bit higher is because, well, those groups were relatively smaller to this one larger group up here that had 75,000 observations, right? So the one that's going to carry the most weight or influence the mean the most is this guy right here. So I'm kind of winging it a little bit today because I wanted to do things a little different. So here's a weird idea. So what we know about the mean, right, and what I was just saying about this value, because the weight is so much higher, is going to influence that weighted mean more, right? So what's one thing that group data actually does a good job of in respect to the mean? That if we just had like a small or regular data set, something that can happen with the mean that wouldn't be as likely to happen with the weighted mean. So we talked about the median and the mean, right? And the mean was more influenced by what? Really big values or really small values, right? Outliers in either direction. Well, here, if I have group data, really, if I had one outlier, it gets factored into this mean, and so it doesn't carry near as much weight. Or think about it this way. Even if I have an outlier, if the group is relatively small, right, it represents a small number of people, well, it's not weighted as heavily, right? So I'm kind of getting those outliers aren't having as large of an influence as they would now it doesn't mean we should just group data all the time because it's very useful to be able to see every single observation, but that is one thing that kind of comes out of this. So I wouldn't say it as calculating the most accurate mean, right? So if you have the data and you aren't able to see every single observation, like it's grouped, it's the best calculation we have for the mean, right? If we were able to see, say, every single person here, every single person's income, we really should just be calculating a regular mean, right? Now, there will be outliers that influence it, but we can think about here, with these observations this high, we said it really won't influence it near as much, right? But it's, if we're thinking about another data set where there's only 4 observations where we don't have weights, then yeah, it's going to be greatly influenced by outliers. Here, when we have just 4 observations, 4 groups, but we have our weights, outliers wouldn't impact it near as much. So it's can't completely compare apples to apples with the regular mean calculation because we're really forced to calculate a weighted mean because of the way the data is, right? I wish I could see every single person's income in this sample, right? When I download that from the Census Bureau, I wish they would give that to me. They won't. They make you kind of do it by different categories. So here I had race and gender. We'll see some others here in a second. Yep. Okay. So go back. So, we could go ahead and calculate that. We get about 53,000. Once again, what maybe had a greater influence here was probably that 59,000 value since the weight was so much higher than these other groups, okay? So if you wanted to by hand, we just did it in Excel, but you could go through and kind of use the same process and find the mean female income here as well. Notice this is always depressing to download this income data because it's very clear we have racial and gender disparities in wage here. So I shouldn't laugh about it, it's sad, but it's very obvious, right, when you download the data. So I broke this down by other categories. So here I did what, gender and region of the country. I forget exactly which states are in which region, but for our sake, it doesn't matter too much. So if I look at this, what region is going to influence kind of my weighted mean the most? If I look at this data set, which region is going to influence my weighted mean the most? Yeah. Yeah, why? Yeah, it represents the largest number of people. We're using that kind of count or frequency as our weight, so it has the largest weight, right? It represents the most people, or the highest proportion of people out of the total number of observations that we have, or total number of people that we have. And I think that's the case for both males and females, right? Yeah. So south here will kind of, and I think that's because Texas gets included in the south there. That's why it's so large. Now, these incomes are much closer together, right? We don't see a lot of disparities across these regions. I mean, they're different, but not near as different as kind of male and female in incomes we see here. But really, the process would be the exact same. So I'm not going to kind of go back through it. I'll just kind of mention it here real quick. But I don't have any like formulas. But you would take the income value we see for the Northeast, multiply that by the weight. Add to that the income value you see for the Midwest, multiply by its weight, so on and so forth. Once we add all those up, we then divide by the sum of our weights, which we had over here. So that was kind of nice. And that's how we could kind of reproduce that 36,000 value. Okay. Any questions on this up to this point? We're okay with this? All right. It's not too bad. Now, if we can do weighted means, we can probably also do weighted variances. Okay, so this is going to be very similar to what we did with variances before, and also why I showed you that first equation, because that's the one that's going to be way easier to use when we do weighted variances, right? So before, what we were doing was we took the deviation of each observation from the mean and squared it. We're going to do that exact same thing here, but then we have one more step, right? When we said the variance is kind of like a measure of the average deviation from the mean, well then, for whatever observations deviation that we're looking at, we need to weight that now by how many people that one observation represents. And I'm saying people because those are the examples that we've looked at. If we have the data instead, like maybe I only have average sales by company, right? So how many stores would that average sales, right? It doesn't have to just be people. It's whatever we're kind of whatever example we're looking at. So we'll weight it by whatever the weights are that we're using. So we still go through every observation, subtract the mean, square that value. We then just have one more step, which is multiply that deviation squared by the weight for that category or that group. And then here we divide by the total number of observations. Here, another way I could write this is, if I copy this, paste it. All right, so it's the exact same thing. But my total number of observations here is actually, I don't know if I can highlight this without, oh, that's stupid. Let's do this in parts. We'll get there, hold on. There you go. Right, that total number of observations is really going to be, I identify that by adding up my weights, right? So that numerator, even though it's the sum of my weights, if we go back to this example, the sum of the weights really represents the total number of observations in that data set before it was grouped, right? The data set I can't see had a total number of observations, which I can calculate by adding up all the weights, okay? So we can think about this guy being our variance equation. So we go back to that data. What I'll do, and I had to kind of race by kind of gender one here. So I'll take every single income. I'll subtract the mean that we found, which if we go back, what was that? 53,000. So I just went through, subtracted 53,000 from every single income value, and then squared it, and then multiplied it by the weight of that group. Once I had all those numbers, I simply add them up, and then divide by kind of the sum, or this would be if I added them all up and then divided by the sum of my weights. Right? So I'm going to show you how we would kind of recreate something like this in Excel right now. Okay. So go back to kind of here. I'm going to delete this. Well, I want to make sure we can see. I'll just grab the original data. We'll kind of come down here. Okay. So before, we found the weighted mean right here, right? So that might be useful because when we want to do the variance, right, this new column we're going to create is the weight times the deviation from the mean squared for every single observation, okay? Once we do that, we're going to add them all up and then divide by the sum of our weights. And that's what the equation says. So what we'll do here is take the weight, multiply that by this observation's value minus that mean squared. That's what we wanted to do for every single observation. Take the deviation from the mean, square it, and then multiply it by that weight. Now, when I copy this down, I want these values to update, but I want to keep using the mean, so that's going to be a cell reference we need to freeze, okay? But once I have this for every single one of my observations or every single one of my groups, the only thing I have to do from there is add all those up and divide by the sum of my weights. So these are really big values. Notice like it's in scientific formula, so it means, I don't know if we've gotten here yet, but this means, if you ever see this in Excel, it means e to the whatever. If it's positive, it means move the decimal 11 places to the right. If this was like e to the negative 11, it would mean move the decimal 11 places to the left, okay? So we'll copy this down. We now have every single one of our deviations squared multiplied by the weight for that group. Notice our cell references here are correct. We froze the right thing. Okay, everything's working good. So to get our numerator, we need to add up all those deviations squared times their weight, right? So we'll use that sum function, add them all up. The only other thing left to do is take that and divide it by the sum of the weights. I could break this down into some steps here. So I could do, first I'm going to add up the weights, right? If I want to make this a little bit clear for us, it's the total we have right here. So then to get my weighted variance, I'm going to take those sum of the deviations squared, that would represent my numerator, divide by the sum of those weights, and hopefully, that should give me, right, my weighted variance, okay? Any questions that you want to see a cell again, or, okay? So that should be the value that we just recreated right there, right? Let's double check, 15,000, yeah, that's the one that we just calculated. So you could do the same process and find the male kind of variance. That's the one that I had in the slides here. I didn't have kind of completely all the work behind it, but here we just kind of walked through one where we could reproduce that female variance as well, okay? Here's an interesting, so I have this weighted variance. It's still a measure of the variation that exists, but it's trying to capture not the variance that exists across these kind of races. It's trying to reflect, because we're using these weights, it's reflecting the variance that exists in the original data as well, right? So here I've got, for male income, a variance of 94 million, and for female income, I have a variance of 15 million. So what's that telling me if I tried to kind of put that into presenting this as some, what do those statistics tell me about male and female income based off this sample? If female variance is lower, what is that saying? I mean, variance is a measure of variation in the data. Yeah. It's closer together? Yeah, so we would say that female income deviates or varies less from that middle point or from their mean, right? Now, we're not saying, we're saying within kind of female income here, we see less variation than we see in kind of male income values, okay? Now, why that is, we could dive into some, probably a million different reasons we could dive into, but at least just from those basic weighted variances, we're seeing there's more variation kind of in our male data than there is in our female data, okay? Or male income than female income, okay? We could do the same thing by region, and it kind of reflects the exact same idea. There's kind of less variation in female income than there is kind of male income. That it kind of plays out when we calculate the weighted variances by region as well, right? And once again, same exact processes that we were doing before there. It's just we've got some different values. So if you want to play around with this and just kind of use these values as a way to kind of check to make sure you can, using your calculator, or if you want to try to learn how to do it in Excel and get good with it that way, make sure you can kind of reproduce these numbers. This would be some good slides to kind of use as reference. Okay. I'm going to do a really basic example of the weighted mean too, just in case we're not convinced, and we'll kind of end on this. So I like this example because we start to think about, we can really highlight why these weights are important. So let's say, I don't know, I've got a portfolio and I've invested like $900,000 into one stock, and I've only invested, I don't know, $1 into the other, right? And I think about the return, if I can spell, the return on each one of these stocks. Maybe the stock or the mutual fund I invested in that, you know, had a, that I invested $900,000 on, maybe I saw, I don't know, a negative 2% return, right? And maybe the one I invested $1 in, I saw 100% return, right? Well, that could be really misleading. If I didn't look at the amounts invested, right, I'm going to think that my average return here would be what? If I'm doing the math in my head correct, 49%, 100 plus -2 divided by 2, yeah, it should be 49%. But if I look at this and you tell me that this portfolio has a 49% return, I guess technically you're right in terms of the stocks you invested in, but I only had $1 invested in the stock that returned 100% and $900,000 invested in the one that had a negative return, right? So if I mean, the portfolio, this is going to definitely, you're going to see losses here, right? You know, 100% return on $1 means I now have $2. That's okay. Yeah, you know, that's not going to compensate for the 2% of 900,000 that I lost, right? So really, when we're doing something like this, maybe it's not like the count of people, but it's like the amount invested. So just to clarify, so the amount invested here, right? The weight might look something like this, right? It might not be the number of people that that observation represents, but it might be, well, how much of our you know, if this is an individual, how much of our income, right, was invested in this stock versus this one, okay? So this is another pretty relevant, and I think it kind of highlights like, yeah, it doesn't matter if you see like these values, right? We're not just looking for the mean return between two observations. Those two observations represent very different amounts of money or very different proportions of the overall portfolio that each one of those stocks is. So even though we're using the weights and then dividing by the sum of the weights, kind of that one example I showed you earlier, what we're really doing there is trying to, what we're actually capturing is the proportion of kind of the total observations that one observation represents, or the total amount of money invested, or sorry, the proportion of the total amount of money invested from that one kind of stock or that one return. Okay? So there's another example, another way of thinking about that. Okay. So that should give you a lot, I think almost everything we need with the exception of, I think, the very last question on the Connect we haven't covered yet. We'll get there on Wednesday. We'll do some more mean weighted variance stuff in a slightly different scenario. And then from there, we'll move into measures of correlation and talk about those a little bit Wednesday as well, okay? All right, so next class should be group 2. As I kind of said last week, if you're in group 1, you can kind of see today we have some empty seats. So if you're in the building and you want to try to attend, if you're here, group 2 will have priority, but if there's empty seats, then you're more than welcome to kind of join us, okay? All right, have a good day. Get that online quiz done before the start of next class, and I'll see you guys on Wednesday.